Lecture 3 of The World of Sound by Sir William Bragg. This LibriVox recording is in the public domain. Sounds of the Town. Sounds made in the open air travel away and, for the most part, do not return. Sometimes they do, and we say we have heard an echo, but the effect is feeble compared to the reverberation of sounds made within a room or in the street. A room in which walls, ceiling, and floor are bare behaves to sound in the same way as it would behave to light if it were lined with mirrors. There are countless reflections, and a sound once made rings round the room for a long time afterwards. Curtains, furniture, and all things which break up and absorb the waves of sound reduce the resonance. Sometimes, on entering a house, one notices the difference in sound when the stair carpets are up. Quote, "The late blind Justice Fielding walked for the first time into my room when he once visited me, and after speaking a few words said, 'This room is about 22 feet long, 18 wide, and 12 high,' all of which he guessed by the ear with great accuracy." End quote. Darwin's Zoonomia. The blind are very quick to detect the special resonance of a room and to judge its size thereby. They are very sensitive also to the reflecting powers of surfaces near them, and can tell their nature and how far they are away. Those of us who have sight do not make much use of this power. Nevertheless, if we move about in the dark, we often find that we are relying on it, as when we are conscious of our near approach to the end of a long passage. If we try an empty room, we can find certain notes to which it specially responds. In the bathroom, generally the barest in the house, we soon know the natural pitch of the room. The plashing water calls it out, or the sound of our voices. I think that is one reason why we are so often tempted to break out into song. The keynote is set for us, and the resonance makes us feel we have passable voices. Humiliation awaits us when we get back to the dressing room. When the water has been turned off, the drops still falling from the tap call up quaint little noises which have a peculiar interest of their own. The series of events which take place every time a drop falls into the water is too quick for the eye to follow. But the late Mr. Worthington used instantaneous photography to record what happens, and I will show you some of his results. His method of working consisted in allowing a small metal ball to fall at the same time as the drop of water. The heights through which ball and drop had to fall, and the times of release, were very carefully adjusted. When the water drop arrived at the water surface, or reached the particular stage of its subsequent history of which a record was required, the metal ball at that moment reached a spot where it started a brilliant electric spark. For a very brief moment the water and the drop were strongly illuminated. The camera stood ready and the photograph was taken. By varying the conditions of release of the ball and drop, he obtained in successive pictures records of all the stages in the series of events that took place when the drop fell into the water. In one set, figure 36, numbers 1 to 5, a drop of water containing lampblack is falling into a mixture of milk and water. You can see in 1 the falling drop, in 2 the splash which is thrown up as the drop enters, and in 3 and 4 the subsequent growth of the splash. In 5 you see the column which leaps up a little while later with the original drop on top of it. Figure 36, a drop of water containing lampblack falling into a mixture of milk and water. 1 t time equals 0. 2 t equals 0.0032 seconds. 3 t equals 0.0050 seconds. 4 t equals 0.0165 seconds. These 4 show the formation of the basket splash. 5 shows the subsequent rise of the drop, t equals 0.1 seconds. Footnote: let the reader, when he next receives a cup of tea or coffee to which no milk has been added, make the simple experiment of dropping into it from a spoon, at the height of 15 or 16 inches above the surface, a single drop of milk. He will have no difficulty in recognizing that the column which emerges carries the white milk drop at the top, only slightly stained by the liquid into which it has fallen. Worthington's A Study of Splashes, Longmans. End footnote. When photographs are taken from below the surface, it becomes clear that an air cavity is often formed. In figure 37, for example, we see the cavity formed behind a shot which has been dropped into water. Figure 37, a shot falling into water leaves a cavity behind it. Now it appears that the note which we hear is the resonant note of this cavity, probably given out when the cavity has closed over at the top and burst again. My friend Sir Richard Paget has actually measured these cavities in various cases and then made models of them in plasticine. Blowing across the top of the model cavity, he finds that its note is practically the same as that which the drop makes when it falls. The note is very high and has a frequency of 2,000 to 3,000 vibrations a second. Figure 38, dome forming over the cavity made by a rough sphere falling into water. Worthington showed also that a very clean, dry ball makes little or no splash or noise when it is dropped into the water from not too great a height. Photographs show that in this case the water clings to the surface of the ball and laps round it as it enters. This is shown in figure 39. Figure 39, a smooth, dry shot falling into water with very little splash. 1. T time equals 0. 2. T equals 0.0025 seconds. 3. T equals 0.0080 seconds. A sheath splash. Worthington spoke of this effect as a sheath splash. The more common and noisy effect he called a basket splash. It is easy to understand that there will be no noise when the water closes up over the ball at once, so that there is no cavity behind it. These experiments are very interesting and easy to try for oneself. Bicycle balls give good sheath splashes when they are bright and dry. It is extraordinary what a difference is made if the ball is wet or is rusty or roughened in any way. It is a convenient plan to put a piece of cloth or rubber at the bottom of the basin into which the balls are dropped. Sir Richard Paget observes that there is no noise unless the water is deep enough for the cavity to be formed in it. No doubt the reason why the drops falling in succession under the same circumstances make notes of different pitch is that the form of the cavity is altered by slight changes in the shape of the drop when it reaches the surface, or in the form of the surface itself. A drop oscillates as it falls between a flattened and a pointed form, and the shape of the cavity must depend considerably on what form the drop has at the moment of striking. We have to remember also that the note of the cavity may possibly depend on the size of the opening which it has at the moment of sounding. If we make a model cavity in plasticine and find its note by blowing across the top, we observe that the note falls in pitch when we close in the opening more and more. This last effect manifests itself in many other interesting ways, a number of which were considered by the late Lord Rayleigh and will repay our special attention. Here, for example, are two flasks of the same volume but differing in the size of the opening. When I blow across the mouth, the flask with the narrower opening gives the lower note. A still simpler experiment can be made with an ordinary cigarette holder, which is just a short tube wider at one end than the other. If I close the smaller end with my finger and blow sharply across the wider, I get a much higher note than when I do the same thing with the tube reversed. After all, this is what might be expected. Consider, for instance, a vessel A of the shape shown in the figure. When it is sounding its simplest and deepest note, the air alternately rushes in and out of the opening. When it rushes in, it compresses the air in the vessel, the pressure inside increases, and presently has increased so much that the tide is turned and the air is forced out again. Its momentum carries it too far, and after a time the tide begins to flow once more. The constant repetition of these events constitutes the vibrating motion. Suppose that the same effects were occurring in the vessel B, of the same size as A but having a wider opening, and that the same amount of air was flowing in and out. Then the maximum pressure would be the same as in A, but since the opening in B is wider, the in and out motions of the air are less restricted, and the vessel will empty and refill itself more quickly. The pitch of the note is therefore higher. A good illustration of this effect is to be found in the ocarina. It is blown like a whistle, and as in the whistle there are rows of small holes which may be covered by the fingers. But the shape of the body is peculiar, as the illustration shows. Figure 41, ocarina, 6 inches wide. M mouthpiece, D, E, F, G, holes covered by the fingers of the right hand. The other holes are covered by the fingers of the left hand. The behavior is like that of a flask rather than like that of a long tube. When a hole is opened by lifting a finger and the player blows across the main opening, the air inside vibrates in such a way that it surges in and out of the open holes. If 2 holes are opened, the pitch rises, because the air can move in and out more easily using both at once. If 3, 4, 5 holes are open, the pitch still rises. The curious point is that the pitch depends much more on how many holes are open than on what particular holes they are. If only 1 hole is open, it does not make much difference whether that hole is, for example, 1, 2, 3, or 4. When we go out into the street, we meet with the roar of the traffic. It is curious how quickly we lose it if we turn aside from the main thoroughfare. The houses cast shadows of the sound, and more particularly of the sounds of high pitch, so that in the side streets the sound of the traffic has become muffled. That is to say, the deeper notes only are left. When a car goes by, there is a drop in the pitch of all the noises that it makes. The effect is most easily observed when the pace is swift and the drop is great in consequence. When the fire engine dashes by, the sound of the bell, which is being rung continuously, is obviously lowered in pitch as the engine passes. We may explain the effect in the following way. As the car or the fire engine is coming towards an observer, the sound pulses, which it is pouring out at the rate of so many in each second, run ahead to the observer, whose sense of the pitch of the note depends on how many pulses reach him every second. This number is artificially increased by the movement of the source. Each pulse is given a little handicap on the pulse before it, so that it follows its predecessor at a smaller interval than it would have done if the source had been at rest. It may be helpful to consider 1 or 2 illustrations. Suppose that a man travelling home to London from Rome in a leisurely fashion, 100 or 200 miles each day, were to write daily to a London friend. The friend would, on an average, receive rather more than a letter a day. Or again, suppose men marching in single file up an escalator in a tube station and mounting at the rate of 1 step a second. When the men get to the top, they step off and walk away at their natural pace, past an observer who counts them as they go by. Let him first make a count when the escalator is not working. Then, if the escalator begins to move, he will find that the number passing him in each minute is greater than before. Figure 42. In the upper diagram, the escalator is at rest. The file of men represent a succession of sound waves coming from a point at rest. In the lower diagram, the escalator is working, and the men are now closer together when they pass the observer, though they are marching at the same rate. Just so, in the case of the approaching car, the observer receives more pulses in each second than the car is giving out, and the pitch of the notes is raised in consequence. The increase in the number of pulses received is nearly in the same proportion to the frequency of the note as the speed of the car is to the speed of sound. An accurate calculation can be found in any textbook. Footnote, for example, in Barton's Textbook on Sound. End footnote. If the car is approaching at 25 miles an hour, the proportion is 1 to 30, because sound travels at the rate of 750 miles an hour. If the car is going away from the observer at the same rate, the note is equally lowered. The number of waves reaching the observer in each second is less by nearly 1/30th of their true number. If we compare the note of the approaching car with the note of the receding car, the double change amounts to 1/15th of the true number. This corresponds to a drop in pitch of half a tone, that is to say, from any note to its flat. When an express rushes through a station, the pitch of the whistle of the engine drops about a whole tone, and the drop is twice as much when the observer is in one express and listens to the notes of another that is passing. The drop in pitch is exactly the same for every note that is made by a passing car. The wind makes a very small difference, imperceptible by ordinary means. We might imagine an intelligent and musical policeman listening for the drop in pitch, knowing that if he could estimate it correctly, he would know at once the speed of the car. Of course, we might try to circumvent the policeman if we were driving the car by putting on a little extra speed just as we went by, so as to make the drop appear less, but we should have to be careful not to overdo it, lest the pitch did not fall at all, or even rose. I have been trying to imagine what the policeman would think in the latter case. If he stuck too closely to his formula, he might be led to the conclusion that, in spite of appearances, the car was really going backwards. The effect we have been considering is met with in the case of light as well as that of sound, and it was in fact in connection with light that it was explained by Doppler 80 years ago. The results in the case of astronomy have been very wonderful. If a star is moving towards us, light waves which it emits crowd on us a little too quickly, and the light rises in pitch. That is, it moves a little way along the spectrum from the red to the blue. And by measuring the shift, the velocity with which the star is approaching can be calculated. In the terrific storms which take place on the sun, when masses of heated and incandescent vapour are whirled and blown about at speeds of hundreds of miles a second, the velocities in the line of sight can be measured, and the course of the storm can be followed. It is very curious that by means of this principle it is easy to find the velocity with which a star is moving to or from us when the star is so far away that any motion across the line of sight is imperceptible, just the opposite to our common experience of objects moving on the earth. One of the most interesting of town sounds is the reverberation sometimes found in public buildings, an effect which makes it difficult to hear a speaker. The sounds that he utters go ringing round the room for some seconds and confuse the words that follow after. The walls, ceiling and floor reflect the sound just as the ripples were reflected by the walls of the tank. Suppose, for example, that a sound, let us say a hand clap, can be heard for 5 seconds after it has been made, which is not at all unusual. During that time it has travelled about a mile and must have been reflected dozens of times. The sound lasts longer than in a smaller space like a room, because it has to travel farther before it has experienced enough reflections to destroy it, for there is always some absorption at each reflection. If we clap our hands in a hall when no audience is present, and find that we can hear echoes for more than 2 or perhaps 3 seconds, it is certain that the hall is not good for public speaking. The surfaces in the hall are too efficient as reflectors, and their efficiency must be destroyed before good hearing is possible. This can be done by covering the walls and floor with a sufficient quantity of material which will absorb sound: curtains, carpet, felt, and so on. A long series of experiments has been made in America by W.C. Sabin, who has arrived at certain very simple conclusions. Footnote: Journal of the Franklin Institute, January 1915. End footnote. He found, in the first place, that a given quantity of material, such as so many square yards of carpet or curtain, has the same effect no matter where it is placed, which is what might be expected, because a sound which lasts for several seconds must have hit every part of the room, walls, ceiling, or floor, and have run up against the material at some time or other. In the second place, he found that he could calculate beforehand how long a sound would last if he knew the volume of the hall and the nature and extent of all the various surfaces in it. Given, therefore, the volume of a hall, we know how much absorbing material should be placed in it if hearing is not to be interfered with by reverberation. Of course, reverberation is not the only cause of bad hearing. It may be that the space to be filled with sound is really too big, and is as difficult to cope with as the open air. Or again, the form of the building may be such that sound is dissipated too quickly. There may be too much absorbing material, or too many recesses and openings into which sound passes, never to return. It does not appear to be advisable that a hall should be quite dead. A period of 2 to 3 seconds between the moment when a sound like a hand clap is made and the moment when it ceases to be audible does not seem to be unreasonable, especially if the experiment is made when there are no people in the room. The presence of an audience does a great deal to stop reverberation. A concert room should be rather more resonant than a room for speaking. Sometimes the more distressing features due to too much reflection can be removed with very little trouble. In a very bare and plain room in the basement of the Conservatorium at Adelaide, piano recitals were at first almost impossible, because the room rang with shrill and piercing notes. The evil was practically cured by hanging 2 or 3 strips of serge 2 feet wide from the ceiling across the room. The reflection of sound by the walls of a building leads to curious results in certain cases. One of the best known has given its name to the Whispering Gallery in St. Paul's. Anyone who whispers to the wall on one side of the great dome can be heard by a listener even as far away as the opposite side, provided that he also is close to the wall. Lord Rayleigh gave the explanation of the effect long ago, and later, in 1904, showed in this room an experiment in illustration of it. He pointed out that sound tended to creep round the inside of a curved wall, being continuously reflected by the wall without ever getting far away from it. We will repeat his experiment. A sheet of iron, 12 feet by 2 feet, is bent into the arc of a circle in order to represent a piece of the circular gallery wall. At one end is a bird call, at the other a sensitive flame. When the bird call is sounded, the flame flares, and it is easy to prove that the sound is creeping round the inside of the wall and close to it, because a screen 4 inches wide placed close to the wall, as at B in the figure, or at A or C, cuts off the sound entirely and the flame ceases to flare. If the screen is withdrawn a few inches from the wall, the sound gets through between the wall and the screen, as the flame shows. In fact, the screen is no use anywhere except near the wall, but any point along it will do equally well. Before Lord Rayleigh gave this explanation, it was thought that the sound was focused from one point to another by the dome above the whispering gallery, and that the speaker and listener should be exactly opposite to one another. It is not necessary, however, that the whisperer and listener should be in any particular positions. Moreover, whispering is heard more distinctly than ordinary conversation, especially if the whisperer's face is directed along the gallery towards the listener. Whispers contain a larger proportion of high-pitched sounds than ordinary speech. We have seen that such sounds do not spread sideways so obviously, and are more easily directed and controlled. A whisper which is heard easily in front of the whisperer cannot be heard behind him. The same cannot be said of the sounds of the natural voice. Mr. Child has called my attention to a remarkable echo in the Victoria and Albert Museum. A stamp of the foot on the floor under the centre of the octagonal dome is followed by a number of echoes from different reflecting surfaces which are contained in the structure of the building. We must not forget the bells of London town. Bells are a study in themselves, and we shall have time for only one or two simple points. Their vibrations are of much the same character as those which we can set up in a finger bowl by rubbing it along its edge with a wetted finger, or drawing a violin bow across it. Here is a large plain glass bowl which Tyndall used. It has a glass stem by which it can be held. 4 pith balls suspended by fine silk threads rest against the edge at equidistant points. Figure 45A. Figure 45, the pith balls, which ordinarily rest against the bowl, are flung outwards if the bow is drawn across the rim close to one of the balls A, B, C, or D. But they do not move if the bow is drawn across at E, F, G, or H, that is, at points halfway between the balls, because then the balls rest against the bowl at nodes, or point of rest. If I use the bow to excite its main note, we see how the pith balls are flung out and away by the vibrating glass, figure 45B. But the effect depends greatly on where the bow is drawn over the edge. If it is at a point halfway between two balls, they scarcely move, because in fact the points where the balls touch are now nodes. The rim of the vibrating bell alternates between the two forms shown in firm line in figure 46. There are 4 points A, B, C, and D where the rim moves in and out most, and 4 others, E, F, G, and H, where it does not move in and out at all. One of the former always coincides with the place of bowing, so that if the bow is drawn across the edge near one of the pith balls, they all fly out, but if halfway between 2 of them, they are all still. The 4 points on the edge, E, F, G, and H, are not altogether at rest. They really vibrate to and fro along the edge, and if a wet finger is used to excite the notes in a finger bowl, it will be observed that there are no ripples just opposite the finger, because the ripples are due to the in and out movement of the glass, and there are no such movements underneath the finger. The bow is drawn across the edge of the bowl, but the finger is generally moved along it. The ripples caused by the bow may be so violent as to break into showers of spray. When we come home to our own fireside in the evening at this time of the year, There are pleasant sounds to greet us in the singing of the kettle and the sounds of the chimney up which the flames are darting. The sounds of the kettle are very interesting. The bottom of the kettle, where the flames touch it, is the hottest part of it, and it is there that the water first rises to the temperature at which steam is formed. The little bubbles of steam are at first at a pressure strong enough to stand the pressure of the surrounding water, but as they rise to the surface and come to the colder parts of the water, their temperature falls and their own pressure with it. There comes a moment when they can no longer hold up against the pressure round them. They collapse, and do so with the greatest suddenness, so that the sides strike against each other with a sharp smack. The blow is as hard and unyielding as when steel meets steel, and so there arises a noise from the kettle as if blows were rained upon it by innumerable tiny hammers, because the water carries shocks of this kind to the metal walls, and the blows might as well have been given to the walls themselves. We shall meet with this effect again when we come to consider underwater sound. The kettle stops singing when the water all through has reached the boiling point and the bubbles rise to the very top without collapsing on the way. Drops of water hiss if they fall on a surface hot enough to turn the water into steam. I do not know of any thorough explanation of how this happens. Hissing noises are caused by very rapid vibrations, so that somehow small but rapid fluctuations are taking place where the water comes near to the surface. If the water actually touches the surface for a moment, there will be a sudden formation of steam, so sudden as to have the effect of a small explosion, and this will start a sharp pulse in the air. The water will be lifted up, fall and touch again, and so on. In the multitude of minute explosions due to the many contacts of the water with the hot surface, the explanation of the hissing is no doubt to be found. When the frying pan is on the stove and spluttering noisily, the sound is due, I believe, to the explosions of small drops of water. The melted fat is much hotter than boiling water, but little drops of water remain suspended in it in the liquid state, although they should have turned into steam at a lower temperature. It is a well-known effect. As a matter of fact, the drop wants something to start the conversion into steam. When the laboratory worker finds that water or some other liquid has got past its boiling temperature and yet will not begin to boil, he drops in a lead shot or anything with a roughened surface which will carry down a few minute bubbles of air. The boiling then begins at once. But little drops of water contained in the melting fat are wrapped in the smoothest of envelopes, and it often happens that they rise in temperature until their boiling is long overdue. Something or other starts it, and then the drop boils so fast that its sudden conversion into steam has all the effect of an explosion. The roaring of the wind in the empty chimney is, after all, only the result of its blowing across the top. It makes a noise just in the same way as when one blows across the end of an empty tube, and the notes we hear are very deep because the chimney is so long. A fire makes a confused noise because the heated gases flaming upwards tear the air into multitudes of tiny eddies as they flicker to and fro. Neither of these sets of noises is very powerful in itself, but the combination of a flame and a tube may, under certain circumstances which do not often occur in practice, be the cause of very loud sounds indeed. It is easy to provide these special causes, and the results are very interesting and instructive. Let me describe first of all a very old and simple experiment. Here is a glass tube 18 inches long and half an inch in diameter, and a long tapering gas jet at the end of which a little gas flame is burning. I pass the flame up the tube, and when it is 3 or 4 inches from the bottom it begins to sing with a steady musical note. It is often called the singing flame. The note is that of the tube, in which the air is vibrating in the simplest manner possible to it. There is a node or quiet point at the centre, while at the two ends the air pours in and out. The motion must be considerable because the note is loud, and we have to explain how the flame manages to keep the vibration going. The answer to this question is that the flame itself is fluctuating, large and hot one moment, small and not so hot the next. The fluctuations keep pace with the vibrations of the air in the tube, and are compelled to do so, in fact. And the secret of the effect is that the flame, when it is hot, supplies extra heat at just the right moment to make the air in the tube expand and push itself out when it ought to be doing so. I will try to make this clear by a simple example. Figure 49 shows a bulb containing air fixed by means of a cork to one end of a U-shaped tube containing mercury. Inside the bulb is a spiral of fine platinum wire through which a battery can send a current of electricity, raising it to a bright red heat. The current runs from one end of the battery by way of a wire passed through the cork, goes through the spiral and down inside the U-tube by means of a wire which just dips into the mercury. Then the current runs to the other end of the mercury and out by a wire which dips well in, and so back to the battery. As soon as the battery is connected, the spiral becomes hot, the air inside becomes heated and expands so that it presses the mercury down on the bulb side. But this breaks the electrical connection, because the mercury drops below the wire, the spiral grows cold, the air contracts, and the mercury comes back. The same series of events then repeats itself. You see that the mercury is soon oscillating violently. The point to be observed is that by means of the application of heat we have set a mass of air into regular vibration, just the same thing that happened in the case of the singing flame. But here the motion is so slow that we can watch it and puzzle out for ourselves how the heat manages to keep the vibration going, and the conditions under which it can manage to do it. The principle is so important and has so many parallels in other subjects that it is worthwhile to examine it very carefully. The important point is that the heat is supplied to the air in the bulb mainly when it is expanding. Heat tends to make the air expand, so that the heat encourages it to do what it is already doing, and therefore the motion is increased. Just so, if you are giving someone a swing, you will always increase the extent of the swing if you push him the way he is already going. You will stop him if you push in one direction when the swing is going in the opposite direction. In thinking how this is to apply to the experiment before you, there is one more thing to realize before the explanation is complete. I said that heat is applied to the bulb mainly when the air is expanding, but it is not applied only when it is expanding, for the reason that it is very difficult to arrange that it should be so. And in fact, in the case of singing flames and parallel phenomena, the word mainly must of necessity be used. The spiral warms up as soon as the mercury on the right-hand side in its upward rise touches the dipping wire, and there is still much upward movement to take place and much compression of the air. All this is to the bad. The heat is applied when the air wants to contract. But the wire does not get hot at once, and what is more, on the following downward move the wire remains hot for a moment after the connection is broken. So, on the whole, there is more heat supplied to the air when it is expanding than when it is contracting. It is absolutely necessary that this should be so if the vibration is to be maintained. Now let us see how this condition is satisfied in the case of the singing flame. When the air in the tube is vibrating, the gas in the supply tube is vibrating in sympathy, so that it comes out in gulps, and the flame is alternately large and small. The gas rushes out fast when the air in the lower half of the tube is moving up in the course of its vibration to the node in the centre, and the air in the top half is moving down. The heat of the big flame comes, just as in our model, mainly when the air is expanding from the node. On the whole, it helps the air to expand just when it ought to, and that is how the vibration is kept up. Now let us try with a tube of some size, more like a real chimney. Figure 50 shows one about 15 feet long, hanging vertically from the roof and so arranged that we can conveniently push a large Bunsen gas burner up it. The gas burner has been specially lengthened in order that this may be done. Even when the burner gets near to the mouth of the tube, we hear a noise due to the gas flames, which are fluttering wildly and are torn by the draught now rushing up the tube. This kind of noise is such as we actually get when the flames roar up the chimney. But when the gas burner is well inside, 2 or 3 feet from the opening, the effect I have been trying to explain manifests itself gloriously, and the tube breaks out into peals of banging thunder. Another tube hangs alongside, which can also be made to sing, but not exactly in the same way. About 18 inches from the bottom, a piece of gauze is fixed across the tube. A gas flame is pushed up sufficiently far to play on the gauze and make it red hot. We withdraw the flame, and then, after a moment's waiting, a strong, steady note issues from the tube and continues for a minute or so. In this case, the air rushing past the gauze towards the node, during the time when the air in each half of the tube is moving towards the middle and making a condensation there, draws heat from the gauze as it goes by. But it may be said the same thing will happen in the other half of the vibrations when the air is expanding, and so heat will be extracted from the gauze at the wrong time as well as at the right. We have to take into account, however, that there is a draught up the tube all the time. The air really moves in leaps. It is always a new lot of air that rushes past the gauze and takes the heat to the middle. When the house is still at night, there are odd creakings, many of which are due to changes of temperature. Parts of the house structure shrink more than others as they cool, and a strain is set up which gives way suddenly. In hot countries, wherever houses have roofs of corrugated iron, the sound due to the contracting roof is very common. A stove creaks sometimes after the gas has been turned off, or the cinders as they cool in the grate. There is a great statue in Egypt, near Luxor, which, about the beginning of our era, used to emit a sound in the early hours of the day, when the sun first shone upon it. Pilgrimages were made to hear it. Names of proconsuls and others are inscribed upon the legs of the statue. It was a ruin even then, and it is now suggested that the sound was due to the ringing note of one stone sliding on another, the heat having caused the stone to expand and strain until at last something gave way. Eminent archaeologists differ on the point, some saying that the noise was made by a priest hidden in the stone, but I think that in the beginning the effect must have been natural, though the priest may have assisted nature when some important visitor was waiting to hear, and it was advisable that he should not be disappointed. End of Lecture 3.